This video shows the requirements, the calculation, post-hoc testing, effect size calculation, and interpretation, as well as reporting the results for the repeated measures ANOVA in R. Its purpose is testing the means of the same individuals at 3 or more points in time for differences. For example, I want to see how good a 3-week exercise plan performs. That means before implementation, I record the physical condition in some form of a test score, which is often considered as the baseline measurement. After the conclusion of the 3-week exercise plan, the same test is performed again and a final time after 3 more weeks. I use the repeated measures one-way ANOVA to test for a difference in the average test score over time. The requirements for the repeated measures ANOVA are the following: 3 or more measurements for the same individuals, a dependent variable on the interval or ratio scale, normally distributed dependent variables for each measurement, and equal variances of the differences for the measurements, also called sphericity. First question: what has to be approximately normally distributed? It is the dependent variable for each point in time a measurement has been taken that should be normally distributed. There are 3 possible ways to test this. First, an analytical test like the Shapiro-Wilk test. Second, a histogram. Or third, a QQ plot. The Shapiro-Wilk test is oversensitive to unimportant deviations from normal distribution in large samples. This is a phenomenon for all analytical tests, for which you can find a source in the video description. A QQ plot is the easiest to interpret, therefore we continue creating one for each measurement. For that, we load up the ggpubr package and use its ggqq plot function. Start with your data frame, followed by the dependent variable in quotation marks, and eventually the argument facet.by equals and your time variable in quotation marks. The interpretation of the QQ plot is straightforward. The dots represent the standardized measurements and the line the perfect normal distribution. Therefore, the distances between the dots and the line should be minimized. Again, there will be acceptable deviations, especially on the edges of the distribution, meaning the upper right hand and the lower left hand corners. In my example, deviations in both of those corners can be a bit problematic. If you are in doubt, you might consider going with the Friedman test, which is the non-parametric alternative to the repeated measures one-way ANOVA, and for which I have linked a playlist to go from A to Z. Before starting, please make sure your data is in the so-called long format for the analysis to work. As a first step, I want to see some descriptive statistics to get a first idea of my data. One can use the convenient dplyr package and pipes. Start with the group by function and put in your time variable. Here it's simply time. Follow this up with the pipes operator and use the summarize function for mean and standard deviation on your test variable. Here it is simply called value. My baseline shows a mean of 24.3. The first follow-up measure shows a mean of 27.3 and 28.4 for the second follow-up measure. The standard deviations are somewhat comparable, showing a rather low spread. You can also visualize the distributions for the 3 measurements using box plots. The interquartile range is represented by the height of the box and the median by the black horizontal lines respectively. If you have circles above or below the whiskers, those are values that have the 1.5 times interquartile range distance to the edges of the box and are sometimes referred to as outliers. If those are plausible values, you have no reason to worry. Now I finally want to test whether the means are significantly different from each other. I use the ANOVA_test function of the R statics package. For convenience, I'll save the results into a vector, for example RMA, repeated measures ANOVA. Within the ANOVA_test function, I start off with the data frame. The argument dv represents the dependent or test variable. The WID argument is the ID variable that is required to properly match the measurements to individuals in long format data. Finally, the within argument is the time variable, simply telling R at which point in time the measurements were taken. After the calculation, you will see in your environment that a new vector is appearing, which is called RMA in my case. As promised, I will now test for sphericity. I can simply address it in my vector by calling $ and Marshally's test for sphericity. The null hypothesis for this test assumes equal variances for the differences. If its p-value is above the predefined threshold, you can observe sphericity in your data. In case you can't, the ANOVA will automatically apply a correction for non-sphericity. The interpretation of the corrected results is identical to the non-corrected results I will now provide for my example. To get my results, I will place my result vector into the get_ANOVA_table function and run it. The interpretation is straightforward. Look at the p-value. If it is below the predefined threshold, for example 0.05, the null hypothesis can be rejected. Reminder, the null hypothesis here assumes no differences for the means between the measurements over time. In my case, I defined alpha as 0.05 and can therefore reject the null hypothesis because my p-value is very small with 1.06 times 10 to the negative 7. I can therefore conclude that the means over time are different. After a significant repeated measures one-way ANOVA, post-hoc tests should be calculated. To achieve this, pairwise comparisons are being done. Those are simply multiple paired t-tests. I'll use the pairwise_t_test function of the rstatics package in combination with pipes. I'll start with the data frame and add the pipes operator behind it. The next line is the pairwise_t_test function that has the dependent variable, followed by tilde, that small wave symbol, and the time variable. The paired equals true argument needs to be added since you have repeated aka paired measures. Finally, the p-adjust method argument is required to counter the alpha error inflation caused by multiple pairwise comparisons. The easiest and also most conservative one is Bonferroni, where your p-value will be multiplied with the number of pairwise comparisons being done. Other methods like Holm, FDR and so forth can be found in the documentation of the pairwise_t_test function and used accordingly, albeit your choice needs to be justified, at least with research field specific standards. Eventually, we get a table that shows all pairwise comparisons. In the last two columns, their respective adjusted p-values are shown as well as significance indicators on the 5% alpha level. In my example, I can observe a difference between T0 and T1 and T0 and T2. This indicates a working intervention, in my case, an exercise plan. There is also no further increase or an immediate bounce back since T1 and T2 show no difference worth mentioning. Please consult the paper, the ASA statement on p-values and draw your own conclusions dichotomizing decisions based solely on the p-value compared to the alpha level. Finally, you might have a significant repeated measures one-way ANOVA and no low enough p-value in post-hoc testing when controlling for alpha error inflation. That is not a contradiction, and the internet is full of discussions about this phenomenon on significant tests and non-significant post-hoc tests. Just keep in mind that a p-value, to which it all boils down to, is a function of sample size, which decreases with an increase in sample size for any effect size that is different from 0. So a non-significant test result in almost all cases tells you you're lacking statistical power as a result of too small of a sample. Don't, however, do post-hoc power analysis to justify your non-findings, because the observed power is a one-to-one function of the p-value. After doing post-hoc tests, you should calculate the effect sizes for observed differences. It is common practice to calculate the effect size d after observing differences in pairwise t-test. First, make sure the rstatics package is loaded. Then, I'll start with the data frame and add the pipe operator. The next line is the Cohen's_d function that has the dependent variable followed by tilde, the small wave symbol, and the time variable. Don't forget the paired equals true argument. The effect size can be found in the column f size. Please note that effect sizes will always be reported as positive values. The negative sign is caused by the order of the measurements. Finally, you have to classify the magnitude of the effects for which you consider the p-value being small enough. I already mentioned that dichotomizing the decision against the null hypothesis by strictly looking at the p-value should be avoided. The magnitudes provided here are from Cohen 92, a power primer, page 157. If the effect size exceeds 0.2, it is a small effect. If it exceeds 0.5, it is a medium effect. And if it exceeds 0.8, it can be classified as a large effect. In my example, I have two significant effects that are classified as medium or moderate effects. However, please check if similar studies in your research field exist and compare your effect size with the given ones. If no comparable studies exist, use the common thresholds within your research field. If those are also non-existent, you can always refer back to Cohen 92, a power primer. When you're done, you have to write up the results. First, one formulates whether the measurements are different or not, providing the test statistic alongside the degrees of freedom as well as the p-value from the ANOVA itself. The effect size for the ANOVA is optional but should be added for fellow researchers. In case of calculated post-hoc tests, the observed group differences with a small enough p-value are reported. When you were able to observe an effect, report the calculated effect size d. Finally, the magnitude of those effect sizes are classified with, for example, Cohen 92 or the respective research field specific thresholds.